what did we talk about last time? We kind of finished off the kind of like regularization and line search story in the context of constrained optimization, right? So we talked about merit functions and how to do line searches when you have constraints. And we talked about kind of this idea of like duality and the fact that the Lagrangian thing with constraints is actually a minimax problem. And so the solutions to the KKT conditions are actually saddle points, right? Where you're kind of minimizing with respect to the x's and maximizing with respect to the lambdas, right? So that was kind of last time we did this kind of duality kind of conversation. We did merit functions and line search kind of ideas. And that was the end of our conversation on like general optimization kind of crash course stuff. And that's pretty much it. You can actually write a legit optimization solver now, and you're kind of like doing that on your homework, but that's it. Like that's kind of it. You can actually write an MPC solver now, and the QP solver you do on your homework, like you can actually use that for real stuff if you want to, modulo like implementing it well, right, and making it fast and whatever. But yeah, that's the real stuff. Okay, and then we did this little like kind of interlude on control history, right? And that's just kind of for fun and trying to give you a little bit of like historical background. I think my pacing was not great, and we kind of were a little slow, so we had to cut that short a bit. But I posted on Piazza. You can go back and look at last year's version of that if you want to like see the last kind of third of it that I kind of skipped. And just in the interest of time, because that was just for fun, I'm not going to like go back and do it again today. But yeah, feel free to watch like last year's on YouTube if you want to see the rest of it. Cool. Any questions about any of that stuff? All good? All right, so here we go. Today, we're gonna start actually doing like the real topic of the course. And we're gonna get in first, we're gonna talk about deterministic optimal control. Kind of lay out what this control problem is in kind of precisely in math. And then we're gonna kind of spend some time thinking about that. We're gonna talk about the Pontryagin minimum or maximum principle, depending on your persuasion. And then, hopefully we're going to get into then as a special case of all this, we're going to talk about introduce the LQR problem, which we'll spend a lot of time on and is awesome and super useful. Okay. Anybody? Everybody feeling good? All right, let's do it. So, first order business, this deterministic optimal control problem. So first, we're going to state this in like kind of classically the way it's stated in continuous time. We're going to kind of do this once and then kind of never again. Because as I sort of told you at the beginning, when we were doing all that like dynamics conversation, we're pretty much going to do everything here in discrete time. I want you to know what it looks like to transform the problem into discrete time, i.e. how to use like a Runge-Kutta method and like a little bit about dynamics, but that's kind of, we're going to live in discrete time generally, but we're going to at least introduce it like this, because this is, you'll see this, right? This is like the more or less standard classical way of doing this. So we're going to minimize a cost function with respect to a trajectory. So we've got a state trajectory x and a control trajectory u. And the thing we're going to minimize, this is the cost function. We usually write this as j of x and u. And remember, this is sometimes called a functional. It's a function of functions in some sense. So this j cost function, it depends on x and u, but it depends on these x and u trajectories, right? And these are functions of time. So that's the cost function. And the way in which it depends on those trajectories is as follows. So we're basically, the idea is we're going to write down something called a stage cost. So this is a cost that you incur at each time, at each instant of time or each time step in discrete time. We usually write that as little l. And this is a function of a particular x and a particular u at a particular t, or a particular discrete time step k. And then the idea is we add that thing up along the trajectory. It's called stage cost, and it's added up along the trajectory. So here that looks like an integral. If we do it in discrete time, it's a sum. You're just summing up every This thing gets summed up at every time step. And then in general, you also have what's called a terminal cost or a final cost. So we'll write that as L sub F for final cost or terminal cost. And that's just a function of the state, because at the final time, there's no more control moves. And it's just a function of where you ended up. So this is a function of X at T final. Cool. And so, yeah, we're going to integrate this from T naught to T final, the stage cost, which depends on both the state and the control. And then this is what we call a finite time problem. It has an end time, right? And when you get to the end, you don't have any control moves left, and you just incur this like final cost at X final. So let's maybe write some of these things in. So these are state and input trajectories. This thing is the cost function. And if I wanted to write this the other way, I could just throw a minus sign in front of J and turn that into a max, and it's exactly the same problem, right? So it's a matter of taste. The guy inside the integral here that gets added up over the trajectory is called the stage cost. And then the sort of cost you get on the last state that doesn't depend on the controls is called the terminal cost. Cool. And then we have some constraints. This is a constrained optimization problem. And the first and most obvious constraint that you always have are the dynamics. So we have a constraint x dot of t equals f of x u. So we call this the dynamics constraint. What kind of constraint is it? Yeah. It's actually a set of equality constraints. It's a whole bunch of equality constraints that are enforced at every time, right? Every time. So in discrete time, there's a whole bunch of equality constraints, right? A stack of them. And then we can also have all kinds of other constraints. So like common ones would be actuator limits, right? Like torque limits, bounds on U, which are inequality constraints, right? And then other common ones would be like, for example, like collision avoidance constraints, right? Which are state inequality constraints. So there can be all kinds of other things, and we'll talk about all that. But for now, we're going to stick with just this. So possibly other constraints. Usually other constraints, actually. Like there's almost always other constraints, right? At least actuator limits in here. Okay, so this is the deterministic optimal control problem. That's like it precisely stated mathematically. And there's a few things to say about this. So first one is you might hear people refer to this as an infinite dimensional optimization problem. Does anyone know what I mean by that? Yeah, so that's right. So this is infinite dimensional in the sense that the x and u here, these are trajectories. They're actually continuous functions of time. So the way to think about that is, if I were to do this in discrete time, I'd have a bunch of sample points, right? I pick a time step and I'd sample x and u at a bunch of finite times, right? And usually we say that that's n time steps, big N. So then the size of this problem in that context would be dimension of x plus dimension of u times big N, right? And that's the number of actual variables in the problem. A continuous time version of this, you can think of it as the limit as big N, the number of time steps, goes to infinity, or as I shrink the time step to 0. And that's the sense in which it's infinite dimensional, right? Does that make sense to everybody? Cool. Okay. So that's kind of an aside. This continuous time version is technically an infinite dimensional optimization problem. Practically speaking, we don't really worry about that too much. Okay, and then the other question here that's a little bit subtle and deep is, what are the solutions to this problem? I mean, it's an obvious answer, but like it turns out to be a little bit deeper. So if I solve this problem, what do I get out? What is the solution? It's a single state input trajectory, right? A single trajectory, and that is the answer. So if I give you a dynamics, and I give you like a goal, a cost function, whatever, I set this thing up, I go solve it. The answer is a single trajectory. That is the answer. how about, yeah, we'll get more into this later, but in particular, the reason I'm like kind of harping on this is the solution to this is not a feedback policy. It's a single trajectory. And the idea is if the world is perfectly deterministic, there's no noise anywhere, and I know everything about the environment and the robot and the dynamics, blah, 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 that's all I need. Like that is the answer. And it's perfectly repeatable, right? I can go, like if I do this in sim, I optimize it, boom, there's the answer. I can just open loop roll out the U's and I'll get the same answer every time, right? And that is the solution. Real life's a little messier than that, right? And so sometimes we want feedback policies, and we're going to talk about that. But just to so you know, right, that is the solution of this guy. Yeah.
Is it a state trajectory or a control trajectory?
Both. Yeah. So in here, right, we're minimizing over both x and u of t, right? So it's both trajectories. They're kind of coupled together through that dynamics thing, right? But in general, yeah, you're going to get both of them, and that's it. That is the answer. Anybody else? Okay, so that's an important thing. This is distinct from the stochastic setting, where in the stochastic setting, the answers are feedback policies, not open loop trajectory. And that's for the obvious reason that in the stochastic setting, if everything's noisy, I can't open loop roll out u and get the answer, get the same answer, right? I need the feedback to stabilize stuff when there's noise. So that's a little bit subtle. And actually, one of the deeper distinctions between this optimal control stuff and RL. In RL, everything is sort of considered in the stochastic setting, and therefore the solutions are always feedback policies. Here we can look at this deterministic setting where the trajectories, open loop trajectories, are the solutions. We can also, though, think about feedback policies in this setting and do stochastic stuff, and we'll do that later. Okay, so other thing to say about this is there's a handful of specific problems of this flavor that have analytic solutions. And we're going to talk about one of the biggest ones, which is the LQR problem, a whole bunch. But in general, there's like basically no, like aside from LQR, there's almost no problems that have analytic solutions here. And so then we're like in numerical methods land and we're doing numerical optimization and stuff. And that's why we talked a whole bunch about how to do numerical optimization. Because in practice, that's kind of what you're stuck doing in almost all cases. So that's worth saying. So handful of problems, namely LQR. And then the final note on this is that this is the continuous time version. We're basically going to state it here, and then we're going to do everything else in this class in discrete time. But you kind of know how to transform them, right? Because when you get the dynamics, they look like that usually. So you have to discretize everything. We've already talked about how to do that, right? So we will focus on the... Okay, cool. Any questions about any of that? Cool. Now we're going to write the discrete time version then. And it's sort of obviously, and you know, there's an obvious analogy, right? All the things you would expect. Okay, so here, instead of continuous functions, we end up with samples. So we have x1 to n instead of x of t. And then we have, it turns out u goes from 1 to n minus 1. And that's just because we have this terminal cost, terminal state where there's no more control moves left. So kind of the standard thing here is we actually have one less control than we have states. And then we have a cost function j that now it's a function of this discrete trajectory. So 1 to n samples, u1 to n minus 1. And now, I mean, it's all kind of stuff you would expect. The integral from before becomes a sum from k equals 1 to n minus 1 of our stage cost, which is evaluated at xk, uk. Again, and I just sum it up. And so my subscripts there are k's, I promise. My handwriting is not great. Apologies. And then we have a terminal cost, L final, that's evaluated at x sub n. Cool. Exactly the same idea. And then we end up with our dynamics constraints as before. And now these look like xk plus 1 equals f of xk uk, where these are like, you know, you do Runge Cutter or whatever to get this guy. And then we might, for instance, have torque limits, right, where we would do sort of like uk less than equal to u max greater than equal to u min. it's worth pointing out these would be for all k, right? From 1 to n minus 1, right? So this is like both the dynamics and these torque constraints, these would be enforced at all the time steps. So these are actually a whole bunch of constraints that you would stack up, right? And then we might, for instance, have like obstacle avoidance constraints or something like that. That might look like this. Collision avoidance, this kind of, so this C might be like, some like, distance greater than some minimum radius from some other object has to stay above some threshold amount, right? Collision avoidance. So that kind of stuff, right? So we would typically call this torque limits or thrust limits, right? Depends on the system. And then this stuff is often what like kind of obstacle or safety constraints look like. Okay, any questions about that? It's sort of totally analogous, right? I just like do Runge-Kutta. I do rectangle rule or pick your favorite quadrature rule in the integral there to turn it into a sum. And then now, whereas before that was an infinite dimensional problem, this is now a finite dimensional problem. As in I can count up, if I know the dimension of the state, I know the dimension of the control, I know how many time steps I have, I can tell you exactly how many decision variables are in this problem. And it's and I can throw this in a numerical solver and plug it in my computer. So that's cool. And some other kind of like lingo things. The samples here, like the XKs and UKs, you can call them sample points, whatever. It is a common like term of art in the biz to call these not points. Has anyone heard that before? Yeah, where'd you hear that from? Okay, yeah. So the not point thing actually comes from splines. Because often, like if you've heard of cubic splines, right? They call them control points or not points, right? That's where it comes from. Because often we use splines to interpolate these guys in the integral and and we'll talk about that later in the class. But you might hear that word, and I don't know, part of the lingo. What else do we say about this? Okay, so yeah, we already talked about, to go from the continuous version to discrete land. We use an integrator, right? We use Runge-Kutta, blah, blah, blah. Which we already talked about. So you know how to do that. And then if you want to go the other way, i.e. if I go solve this on my computer, but then I need to get the continuous version of this after I solve it on the computer, what do I do? Any ideas? If I use some suggestive language. So like if I go solve this with like 100 not points, let's say I sample this pretty coarsely, right? Which is common to do because the coarser the sampling, the smaller the problem is, the faster I can solve my computer. So let's say I have 100 dot points. I sample this at like 5 hertz, but then I go run this on my robot and say I need to actually send it commands at 500 hertz. So what I want to do there is like kind of upsample this thing in some sense. That's what I mean by this, right? I maybe, so what do I do there? Yeah. Good of function spline, that's kind of the right thing. The word for this is interpolation. So often what we do actually when we solve these, and we're kind of glossing over this right now, but it's kind of implicit in all this stuff, is usually we have these not points, but in between the not points, actually in the integrator and in the integral there, we're actually interpolating all the time with a spline. It's very common to use cubic splines, right? We use that all the time. So what that's actually giving you though, on the output of this, you're not just getting the XK, UKs, you're actually getting a nice smooth interpolating function that lets you evaluate the points in between the not points in a nice way. And so that's actually super, super useful. It lets us solve this at like a very coarse discretization, but then upsample it, interpolate it to much finer, time sampling after to do other things with. Yeah, this is subtle. This is a good point. Yeah, so it turns out we can form those dynamics constraints pretty explicitly in terms of a spline, and that's very common to do, and we're going to do it in here. You already did it. It turns out RK4 that we talked about is actually interpolating with a cubic spline under the hood. it wasn't obvious maybe the way we did it, but it turns out the derivation of it is basically to stick a cubic spline in and then like analytically integrate the cubic spline by sampling it at 4 points or whatever. That's kind of how you derive it. So there's always kind of anytime you do any kind of higher order integration, there's already kind of implicitly a spline in there. And so embracing that, we can actually use that for a whole bunch of things here. That's really nice. Cool. Okay. And yeah, there is some subtlety in enforcing constraints. So like typically we'll just enforce it on the not points like you see, but if there's stuff going on in between the not points, for instance, if you have collision avoidance constraints, if you just check for the collisions at the not points, it's very possible to have collisions occur in between the not points on the interpolant. And that's actually hard to check. And there's ways to do it, but it's all kind of messy and expensive. So often we just don't bother and we are a little fast and loose with it. Okay. Any other questions about this? I'm feeling good about it. Okay. So this is like the practical version that you're actually going to solve in your computer. And now we're going to kind of take a little detour through a topic that you've probably heard of that is historically important, but I would say practically kind of useless in the modern era, but I feel like it's good for you to know about it. So we're going to talk about it, which is Pontryagin. Pontryagins minimum or maximum principle. We're going to minimize in here, so we'll call it the minimum principle. Who's heard of this before? Handful of people. So what is this for those who've heard of it before? Can you describe what it is? Like, what does it tell you? That's all kind of window dressing. That's just making up words for functions. But what is it actually like doing? What is it, giving you? Why do I care about this? Yeah. Yeah, exactly. So this is the optimality conditions, literally KKT conditions, for an optimal control problem. It's really just KKT conditions. The reason it's a thing is it originally was derived in continuous time. So it's a continuous time first order necessary condition for an optimal control problem. You can also do it in discrete time, and in discrete time, it's literally just the KKT conditions. So kind of the big deal about it is that it's in continuous time. We're going to do it in discrete time here. And then I'm just going to like wave my hands and tell you if you want the continue, I'll tell you the continuous version. So a few ways to get it. The quick and dirty way is to just take the discrete version and like take a limit as the time steps go to 0. So we're going to talk about it. It's historically, again, kind of important, but not really used anymore, practically speaking. So, right, as we kind of already said, this is also called the maximum principle. If you maximize a reward instead of minimize a cost. And it is the first order necessary conditions. For a deterministic optimal control problem. And as I just said, in discrete time, at least, it's just a special case of the KKT conditions. It's just turn the crank on the KKT conditions for that optimal control problem, and that's all it is. Okay, cool. Questions about that? Yeah.
Is this a deterministic optimal control problem?
Yes.
Noise in
Yeah.
our.
Exactly. Specifically, yeah, noise in the dynamics. That's you nailed it. So that's why this is deterministic. What it really means is it's reproducible. Like if you were to like, solve this thing and then go roll it out, if you roll it out 10 times, you're gonna get the same answer 10 times with no variation. That's like really what we're talking about. I would argue, right, if you're doing it in sim, it is, right? If you're doing anything in sim, it is totally deterministic, no matter what the RL people say. If you're doing it on a robot, arguably, right, real world is somewhat stochastic. I mean, if you zoom in far enough, everything is stochastic, right? Because like quantum mechanics and stuff at small scales is stochastic and Brownian motion and blah, blah, blah. But I would say at the macro scale, like if you're dealing with a humanoid robot, like there's noise and stuff for sure, but it's pretty small. And like, I would say at the like 98% level, most of the robots we deal with are deterministic. Like there's small amounts of noise, but they're mostly deterministic. And that's why like these deterministic tools are still extremely useful because like at the 98, 99% level, these things are deterministic and reproducible. And that small 1-2% level noise, we can actually deal with pretty easily with small tweaks to this stuff. So that's kind of where we're going with all this. But yeah, good. Bad. Modeling error is not noise.
It's noise, but then
It's not stochastic. If I have some like my mass is wrong, remember the thing here is reproducibility. If my mass is wrong by half a kilogram, does that change? It's the same every time, right?
yeah. When you move along the dynamics, the estimate of the mass can be very
Can be what?
can be varied. So let's say
Can be sorry,
can be varied.
can be varied. I mean, yeah, the dynamics are the dynamics, right? Like
The model is not complex enough. So let's say if you're
modeling error is not noise. It's deterministic. It's the same every time. That's what I'm getting at. Is that deterministic or is it random?
it's not the
It's not random, right? That's really what we're talking about. So in principle, if I did better sysid, collected more data and fit a better model, that would go away, right? So that's kind of what I'm really getting at here, right? So basically the difference here is that is fundamentally knowable. Like if I tried harder, I could know that and do better, right? And get rid of it. Stochasticity, noise, this is fundamentally unknowable, unpredictable, not reproducible. That's really what we're getting at, right? That makes sense? Yeah. So in principle, if I have model error, I just need to do a better job at modeling, right? And it's actually bad to model those kind of things as noise because there's a bunch of statistical assumptions about, inherent in this stuff that don't hold when it's a sort of systematic kind of error. Like it's actually a bad thing to do. And you should think a little harder about, calibration and sysid and blah, blah, blah. So yeah, thank you for that. That was a very good question. And like, there's a deep thing in there that I see a lot of times people are like, oh, I'm modeling error, I'm going to treat it as noise. That actually can really hurt you in a lot of cases. And yeah. Okay, cool. Good chat. Okay, let's do this. So here's what we got. We're gonna go take like, again, the simplest version of this problem. So just we got our state, we got our controls, 1 to n minus 1. We've got our cost, k equals 1 to n minus 1, stage cost on each time step, and then we've got our terminal cost on the last state. And then we're just going to have dynamics constraints, no other constraints. And they look like this. Cool. So first move, as we've already talked about a whole bunch, we're going to form the Lagrangian for this optimization problem. So literally just put a Lagrange multiplier in there, stick the constraints in there with the Lagrange multiplier. So that looks like, right, Lagrangian. We're going to end up, again, sum 1 to n minus 1. We're going to have the cost. And then we're going to have our dynamics constraint. And there's a particular, I'm actually being very deliberate about my time step indices on here, which, FYI, I don't know. And then we're going to throw the dynamics in here. So xk, uk minus xk plus 1. Right? So it's, constraint equals 0, right? And we throw that in there with a multiplier. And then we've got our terminal constraint. And remember, right, it's not one dynamics constraint, it's a whole bunch of dynamics constraints. It's literally n minus 1 dynamics constraints corresponding to all the time steps. And so we're going to stick it in the sum there, right? So we got a multiplier for each dynamics constraint at each time step, blah, blah, blah. Everyone cool with this? So far, so good. Nothing crazy. Okay, so this is where it gets kind of weird and dumb, in my opinion, but whatever. So this is I'm just telling you words. There's nothing deep about this at all yet. It's literally just notation and making stuff up. But it is how this is sort of the standard way of stating this result. We're going to introduce a new function called the Hamiltonian. Who's seen this before, heard about this before? Yeah, where have you seen this before? Okay, so in control. Does anyone see this anywhere else before? Physics where? Yeah. Yeah, so there's something deep in there. Do you know what that conversion is? So deeper still, what's the transformation called? It's called a Legendre transform or transformation, right? Does anyone remember this? See this in like some kind of physics class? Do you know what that is? It's duality. So the Hamiltonian is the dual optimization problem. The primal one is the Lagrangian, and the Hamiltonian is the dual, which is kind of wild and like subtle, and you don't usually see this in the physics people don't usually tell you this. Fun facts. Okay, so we're going to tell you about this thing called the Hamiltonian. Hint, hint, there's some primal dual stuff going on in here that I'm just teasing it, but there's more lurking beneath the surface if you want to dig in a little bit. Okay, and this is closely related to the physics Hamiltonian, if you've seen that before. Okay, so this thing, again, it's just notation. There's nothing super crazy here. I'm just defining this thing. So it's going to be the stage cost plus the multiplier term with the dynamics. Cool? So it's that. So now I'm just going to take that definition and plug it back into the Lagrangian. Okay, so here we go. So this is now, and there's a little bit of a trick here that I'll explain in a sec. Basically, pay careful attention to the subscripts, the time indices. So what we're going to do here is pull out some stuff from the beginning of the sum and the end of the sum and rearrange the time steps inside the sum. And there's actually a reason for this that I'll explain in a sec. So just pay careful attention. So out here, we're going to pull out h of x1, u1, lambda 2. And then we're going to have the sum on the inside where we've remapped. We're going to start it at k equals 2, and we're going to run it to n minus 1. And inside here, we're going to have h of xk, uk, lambda k plus 1. And then if you just pay attention to what's in here, right, from up above, and what's inside h, we've still got this term lambda k transpose xk that's sort of hanging out. That's not, right? The Hamiltonian includes the lambda f term, but not the lambda xk plus 1 term, right? Everyone see that? So I'm just sticking that still in there. And then we've got some extra stuff at the tail of the sum that we haven't accounted for, which is in particular, we're going to have the terminal cost at xn. And it turns out we're also going to have a lambda n xn. And so there's a bit of like a little index manipulation trick going on here. So I'll write note, change to indexing. And the reason we've done that is to get all the stuff in here to have the same subscript. So in particular, I've got h of xk uk, and then that lambda is minus lambda k xk. So I want those k's to all be the same k. Whereas up here, originally, in the original version of the sum, like they were at slightly different time steps, right? So originally I had xk uk, and then I had lambda k plus 1, xk or plus 1, right? So what I've done is kind of rearranged a little bit and pulled some stuff out at the beginning and the end, such that I've lined those up so that inside the sum, they're all k's. Make sense? And the reason we're doing this is because we want to do first order necessary conditions where we do take the derivative with respect to xk and lambda k and blah, blah, blah. And I want to line the time steps up nicely so that when I do that, I get nice equations. That's why. Fun fact, that index manipulation trick in continuous time is integration by parts. So everyone like suffered through calculus, remember doing integration by parts and it made no sense and it was weird. Turns out if you discretize everything and turn it all into sums, integration by parts is just this index manipulation trick, which is way easier to see and way cleaner. So if you take a continuum limit of this and you shrink the time steps to 0 and turn these back into integrals, that little indexing trick turns into integration by parts. Fun fact, kind of weird. Highly recommend checking that out if you haven't before. It's all kinds of weird little tricks that like no one taught you in calculus that you wish they had because it's so much easier this way. Anyway, okay, so now we're just going to take all the derivatives, right? Set all the gradients equal to 0, the usual thing. So take derivatives with respect to x and lambda. So here we go. So we're going to do dl. We'll do them in whatever order. So we're going to do dl d lambda first because it's obvious what that should be, right? What should that be? What's that going to spit back? Just the dynamics, right? So that's easy. We already know what the answer should be. So let's do that. So this is dl dxk. If we state it equivalently in terms of the Hamiltonian stuff, that's equal to dh d lambda k minus xk plus 1. And if I kind of go stare at this and like actually do it, we already know what the answer should be. It's going to give me back the dynamics constraint. So it's xk uk minus xk plus 1 equals 0. Cool. So that we expected that answer. All good. Nothing surprising. Now we're going to go take, oh, I messed that up. I meant lambda up here. Sorry. All lambdas. Please tell me when I do stupid things. I do stupid things a lot. Okay, so cool. So that's the lambda derivative. Now we're going to do the x derivative. So dl dxk. And this, if we write it in terms of the Hamiltonian, is dh dxk minus lambda k transpose. If we kind of do this stuff the right way. And this is going to end up being the cost, the stage cost gradient, plus a Lagrange multiplier term. So lambda k plus 1 transpose, this is the dynamics derivative, k, and then minus lambda k transpose equals 0. And then the last one we got to do is the final time step, right? The terminal one. So we've got a dl dxn. And if I just kind of, again, turn the crank, this ends up just being the derivative with respect to it only shows up in that terminal cost. So this guy, and then we've got that last Lagrange multiplier, lambda n equals 0. Okay, so that's it. So we've done so far the lambdas and the x's. We still have to do the u's, right? Okay, so this is, you can just do, turn the crank, take the derivative, and that's fine. And in most cases, that's fine. We're going to do it slightly differently, though, which is kind of because it's the standard way in the literature. And there's a reason why it's done this way. So for the u's, we're just going to actually write it explicitly as a min instead of taking the gradient and setting equal to 0. The reason is that it's super, super common to have input limits, right? We have constraints on u. So writing it this way lets you account for input constraints. That's kind of why. And this is the standard way you'll see it written in books and stuff. For u, we write the min explicitly. To handle things like torque limits. So here's what it looks like. We've got uk equals like argmin over u of h of xk u lambda k plus 1 subject to, I'll write it kind of a fancy way, u in some set big U. So that just means u's in some set. It just means u's subject to some inequalities in a very generic way, right? It's just like read out loud, you'd say, so sort of like, it's like a shorthand for like in some feasible set. For example, like what we've written before, right? But that's sort of a generic, feasible set, whatever, right? Okay, so that's all of it. And yeah, obviously, if there's no constraints on you, then you just take the gradient set equal to 0, right? Like normal first order RC. If you have this constraint, then it's like a KKT thing with some constraints, blah, blah, blah. Okay, that's the whole thing. All I did was take gradients with respect to everything and set them equal to 0. So summarizing, we've got, if I kind of rearrange a little bit and write everything in terms of the Hamiltonian, I'm going to have xk plus 1 equals grad respect to lambda of h xk uk lambda k plus 1. I've got lambda k equals grad respect to x of h xk uk lambda k plus 1. I've got uk is this argmin thing, argmin over u of h xk u lambda k plus 1 subject to u in this feasible set, whatever, with whatever input constraints. And then I've got lambda n equal to derivative, the gradient of that terminal cost with respect to xn. Okay, that's the whole thing. There's some subtle stuff in here that we should talk about. So first off, so the first line, right, xk plus 1 equals blah. That's literally just the forward dynamics, right? If I go back over here, cool. So that's literally just telling me forward dynamics propagation, right? And you'll note, right, like the stuff in H there is, you know, it's xk uk gives me xk plus 1. What about the lambda? Let's think about that for a second. So that's H of xk uk lambda k plus 1. So the dynamics one, the first one, that's going forward in time. Given xk uk, it maps to xk plus 1. The lambda one, I plug in lambda k plus 1 and it spits out lambda k. So that one's going backwards in time, which is kind of interesting. And there's a little bit of a deep thing here in that, look at lambda n. What is that? So that's actually, yeah, but in particular, yeah, so it's a function of this terminal cost. It's the gradient of the terminal cost. Remember, I write down the cost function. I know what that thing is. I can just compute it. But what this is telling me is usually in these problems, I know my initial conditions, i.e. I know the state at time 0, right? So I know the initial state. I don't know the initial Lagrange multiplier. I know the final Lagrange multiplier at time n, because it just depends on the terminal cost. So these problems have this interesting flavor where I know the initial state and the final lambda. And I actually, to solve one of these using these conditions, I have to do, there's inherently some like dynamics propagating forward and multipliers propagating backwards. So they have this like weird bidirectional kind of flavor to them. It's called a boundary value problem, where I know some stuff at the initial time, some stuff at the final time, and I kind of have to like forward and backward propagate information to solve the problem. Kind of a weird thing and kind of interesting, right? There's some deep stuff in there that we'll get into more. So thoughts on anything else you've seen in your lives that looks kind of like this? We've got this idea of like forward and backward propagation, blah, blah, blah. Dynamic programming, yeah, this is related to dynamic programming, but not exactly. There's something like way more. Who's done any machine learning? So it turns out what I just wrote down here in Discrete-time, this is exactly backpropagation in a neural network. And in fact, these conditions were invented, the first derived in like late 50s, early 60s. And like this is where backprop comes from. So you can think about this stuff as backprop through time, right? So each time k looks like think about the dynamics, the f of xu stuff. Think about that as a layer in your network, and you have n layers. And this is giving you like, it's exactly equivalent to doing backprop on gradients. That's what the lambda stuff is. And then kind of forward propagation to sort of like compute your error, right? So imagine you're trying to hit some goal state at time n. I can do a forward rollout through my dynamics, aka inference, right? Run it forward through the network. I can look at my error in hitting my goal state. And then I do backprop on the lambdas, where I'm backpropagating, like, remember what lambda n is? The gradient of the error at time n, right? So it's exactly doing backprop. So this setup here is actually the recipe for doing gradient descent on one of these trajectory optimization problems. If you made F a neural net and made the U's the weights, this is exactly doing gradient descent with backprop on a neural net. Kind of deep, kind of cool. Anyone heard of this before? No. Okay, fun. So yeah, backprop through time if you like. Cool stuff. Okay, so just for fun, for your information, These set of conditions I just wrote down in discrete time, they can be equivalently stated in continuous time. We're not going to do it, but literally just take a limit, right? And you'll get this. And what do we think is going to happen in continuous time? So these, we could call these difference equations, right? These like discrete time things. And if we take a continuum limit, they're going to turn into ODEs. So in ODE land, this looks like x dot equals, it's exactly the same stuff. You're just turning them from these difference equations into ODEs. They look exactly the same. XU lambda, that's the X one. Lambda, remember, it goes backwards. So we end up with an equation for minus lambda dot, which means backward time, you know, in ODE land. XU lambda. And then, you know, this is the same with slight abusive. I got to do something about that notation because okay. And then, yeah, same lambda T final is equal to terminal cost gradient. Cool. So that's it. If anyone's ever looked at like neural ODEs or like these kind of ideas of like continuous neural networks, whatever, that's what you got. Same stuff. Kind of cool. What else to say? So anyone who's seen physics version of this before, can you make the connection to
You get the same effect.
almost? Yeah. So the physics Hamiltonian stuff are the first two lines, right? You don't have the U's in the physics version. But yeah, the physics version, the first two lines. What are the lambdas in physics?
Like that.
No. Well, okay, what do they call them in physics? In physics land, you don't have X and lambda. What are the letters? I bet you didn't. So in physics, that's Q and P. Q being the configurations and P being what? Momentum. Sometimes called conjugate momenta, right? Guess what momentum is in physics? It's a Lagrange multiplier. What is a Lagrange multiplier for? What constraint? This is deep and kind of wild. So yeah, in physics, momentum is actually a Lagrange multiplier corresponding to your kinematics of your system, which is not necessarily obvious, but there's deep connections between all these things, and it's kind of fun. And yeah, primal and dual in optimization. So these are duals here, right? Lambdas. They're called, in optimization, they're often called co-states, or in optimal control, they're sometimes called co-states. In physics, they're, at least in this Hamiltonian, they're momentum, conjugate momenta. Yeah, anything else fun to say about that? I don't know. It's cool stuff. Okay, any questions about any of this? It is what it is. So some notes on this stuff before we kind of try it out a little bit or get in some other stuff. So, so this is kind of, I pointed out all the connections to backprop and whatever. And so this is basically the recipe for computing the gradients and doing gradient descent on an optimal control problem. And historically, that's how people did it. So historically, you would take the continuous time conditions here and like do Runge-Kutta forward and backward or something and try to do this. So historically, like many algorithms were based on integrating those ODEs. Forward and backward. To do gradient descent. And, you know, in modern deep learning, we're still doing that. So, you know, so if you do that, if you do like forward, backward, you know, kind of iteration of those ODEs, that's called an indirect method or a shooting method. And there's lots of variations on these themes, right? Like you can do, if you just integrate those from initial conditions all the way time n, and then integrate the lambdas backwards, and that's it. That's called single shooting or shooting. There's also multiple shooting. There's all kinds of variations on the theme. But yeah, that's how people did optimal control for like, you know, the first kind of 20, 30 years of the field, like 60s, 70s. Called, it means like you stick a minus sign on it and you go backward. So you start at like TF, you have the ODE, right? you evaluate lambda dot, and instead of like, so if I go forward in time, if I've got like, x dot, I do xk plus 1 equals, like x k plus time step times x dot, that kind of thing. Literally just put a minus sign on there. So you'd get like, if I imagine inverting that equation, right, and solving for like xk in terms of xk plus 1 and rearranging, I literally just pick up a minus sign, right? So I get like xk equals xk plus 1 minus time step times x dot, that kind of thing. Make sense? You just flip the sign and go backwards instead of forward with the ODE. So indirect and or shooting methods. And yeah, I kind of said this for a sec. So in continuous time, remember it's actually lambda of t. It's a lambda trajectory, right, in continuous time. And this is often called the co-state. It has the same dimension as the state vector. There's a whole conversation to have about what do those Lagrange multipliers mean? What's their interpretation? It's gonna take us a couple more lectures to get to that because there's some other stuff we gotta check out first. But yeah, the meta point, there's these kind of like indirect shooting kind of methods. They've really like just fallen out of favor. Like we don't do it anymore because they're numerically bad for various reasons. They're a huge pain to get to work. They have all the same problems that gradient descent in deep learning has, where you have like vanishing and exploding gradients and optimal control. That was historically called the tail wagging the dog problem. So they have all kinds of issues, and it's hard to enforce constraints with them and all this kind of other stuff. So we basically don't do it anymore now that we have better computers and we can do better things. In particular, now we do second order stuff with Newton whenever possible because it just works better. Okay. Any questions about any of this before we move on? Yeah. So, I mean, it's really just notation. Like, I'm just trying to tell you what, like, if you go look this thing up in a book, that's what you'll see. Like, this is the standard, convention, notation, blah, blah, blah. It's really just KKT conditions. The sort of the Hamiltonian thing, it's really coming from, it's like inspired by physics stuff. And like, that's where it's coming from. And like, it makes the equations pretty. Basically, there's this kind of symmetry here between these equations, right? Like x dot is grad y of the Hamiltonian, y dot's grad x of the Hamiltonian. There's this like nice kind of symmetry property and like whatever. It looks pretty basically. It simplifies the notation a little bit. And it's sort of like how it's done in physics. There's deeper stuff to say about this too. There's like basically there's sort of a sense in which that thing's like kind of the dual objective if you think about primal dual optimization problems. So there's some stuff there, but really like don't worry about it. It's really just notation. Like it's just defining this thing for convenience and writing this stuff down. So what I did here was write down first order necessary conditions, right? Set the gradients equal to 0. I could do that. So if I got rid of this constraint that says U has to be in some, like U has bounds or whatever, then the answer there is literally just grad respect to U, right? So I just wrote it this way because, again, that's standard. You'll see that in the literature. And it's there. The reason we didn't just take grad respect to U and set it equal to 0 is because we usually have torque limits or thrust limits or whatever. So we keep it like this so that we can account for the limits. That makes sense? That's all. It's just because we usually have constraints on U. And this is, I'm just showing you the way you'll see it. Like this is, if you go look it up on Wikipedia or in a textbook, this is exactly what you'll see. So I'm trying to show you that and where it comes from. It's more just for. Exactly, yeah. If you got rid of the U constraints, like literally then it's just argmin over U of that thing, set the gradient equal to 0, done, right? So you're totally right, that's it. These are the kind of, if you look up the Pontryagin minimum principle in a book, this is what you'll see. And it's kind of conventionally written this way because of the U constraints being super common. Yeah. Yeah, that's a good question. Did I screw that up? Oh, no. Yeah, so that term lambda 2 x2 is not in the Hamiltonian there. Right, because I have the lambda f term inside the Hamiltonian, not the lambda x term. Make sense? So remember up here, I've got, if I look at the Lagrangian, I've got lambda f and lambda x, right? So the Hamiltonian only has the lambda f term. So that lambda x term is outside the Hamiltonian. That's right. We can take this offline. It's like an after class conversation if you want. Yeah. They don't. There's no inequality constraints here. Just dynamics. So there's no complementarity, right? It's only equality constraints. So it's just set the gradients all equal to 0.
So do we have any version of this for the inequality?
No. It turns out this kind of breaks if you try to do inequalities in ways that are annoying.
Remember seeing something like h of x star is then h of x.
Yeah, offline conversation. Yeah, but this is kind of the standard thing. This is it. Yeah.
L with respect to lambda k, is that supposed to be k plus 1? Because it feels like we like misaligned it a little bit when we, yeah, version of 3 there.
Yeah.
Should that be, like looking at L, should that be the derivative of L with respect to lambda k plus 1, which gives us f of xk uk?
I think we're gonna have to do this offline. Yeah. So I'm happy to do it we'll whiteboard it after, but I think we got to keep trucking. I can't do on the fly math that easily. All right, cool. Thanks everybody. Yeah. So definitely come bug me after and we'll dig into this stuff. Okay, cool. So now what we're gonna do is sort of special case this stuff to a really, really important sort of special case that is one of the only ones that has a closed form solution that is uber useful all over control theory, and is sometimes called it's been called the crown jewel of control theory. And this is the famous LQR problem, or linear quadratic regulator. So who's seen this before? Most people. Excellent. Good. So the idea here is it's exactly the same setup. It's just a special case where we have the L linear is for the dynamics. We assume linear dynamics, which we talked about the first week, right? And the Q for quadratic is referring to the cost. So the cost function is going to be quadratic. It's going to look like so. So we've got a quadratic cost on both the states. So we're going to call the weight in here Q. And in general, that can be time varying. So it's Q sub K. It can change over time. And then quadratic cost on the U's. So UK, and again, the R, the weights here can be time varying. And then we have a terminal cost on the states. So that's QN. And, there's sort of a cute thing in here where it's LQR and we use Q and R for the weight matrices. This is the standard notation. So the state cost weight matrix is always Q, the control one's always R. And then we've got subject to linear dynamics. So that's xk plus 1 equals A times xk plus B times UK. Okay, so this thing is, number one, it has a closed form solution. We're going to do it. Number two, it's super useful and shows up everywhere. And if you get nothing else out of this class, you should like somehow get some appreciation of LQR. Reason it's so useful is that you can locally approximate almost every nonlinear control problem as an LQR problem. And that's super powerful and gives you a way of developing like local tracking controllers around trajectories and stabilizing controllers around equilibrium points and all kinds of stuff like that. So that's very powerful. And the other one is this is computationally tractable. I can always do this. I can do this for really large problems with huge state dimension. I can solve it quickly. All the good stuff. And there's also many extensions to this in every direction imaginable. So you can do this for stochastic problems. You can do this for partially observed problems. You can do this for infinite horizon problems, like all the things. There's game theoretic versions of this problem with multi-agent sort of things going on. Yeah. 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 So I wrote the time varying one up here. Actually, oh yeah, you're right. I should have AK, BK, right? Call. I wrote the cost time varying and then forgot to do it on the dynamics. And then yeah, there's okay, so let's see. Many extensions. So you can have, infinite horizon, stochastic, which we'll do later, etc. I left out one important note, which is that, remember we talked about QPs? And for a QP to be convex, what do we need? Hessian has to be positive definite. So a similar deal here. We need the Q to be positive semi-definite. And it turns out we need the R to be strictly positive definite for this thing to have a well-posed solution. There's some intuition where that's kind of obvious. We'll get to it. Anyone know off the top of their head why R has to be strictly positive definite here? Then what happens? No, if it's 0, there's no cost on having control, which means you get unbounded controls. It means the controls will blow up to infinity, right? So if I have a cost on like getting to the goal, and I have no cost on the controls, the solution to that is just like slam the controls to infinity and get there instantly, right? So you get like ill-posed, infinite solutions in that case, which is why that's a thing. Cool. Okay. And a quick note, right, is that you mentioned time varying. Thanks for that. So the version I wrote up here where we have Q sub k, R sub k, A sub k, where the matrices in the problem can vary in time, that's called the linear time varying LTV problem. If it's constant for all k, then we call it time invariant. So if like AK equals some fixed A, BK equals some fixed B, QK fixed Q, RK fixed R for all time, right? And then it's time varying otherwise. Okay. Cool. Okay, so this is a problem that we will get very familiar with. And first thing I want to do is, since we just did this whole like Pontryagin thing, we talked about single shooting, indirect methods, we're going to go solve this problem with an indirect method using the Pontryagin stuff. Again, it looks just like gradient descent and backprop in a neural net. It is exactly the same thing. So I'm going to write out like what we're going to special case those equations here, and then we'll do it real quick. Indirect shooting is what this is called. So again, we're going to plug in we're just going to, we have this up above. We're just going to plug in these dynamics and this cost into this stuff to get the special cased versions. So this is the dynamics. It's just AXK plus BUK. Then we've got lambda K is equal to grad respect to X of this guy. And that's going to be, if I just go and plug it in, it's going to be QXK plus A transpose lambda K plus 1. Then we've got lambda N equals QN XN. And then I've got U. If I this one doesn't have any constraints, right? So now I can, as we were talking about, we can just do grad H respect to U. So this is a little weird. Minus, turns out it looks like this, minus R inverse B transpose lambda K plus 1. Okay. Cool. So that's everything just special cased. And then what we're going to do, and we'll do this in code in a sec, but just to kind of make it super clear what we're doing, we're going to, number one, start with an initial guess for the controls. So we're going to guess this U trajectory. So 1 to n minus 1. Number 2, we're going to do so if we just look at these steps, that first line is a forward rollout through the forward dynamics. So we're going to take the guess. We're going to simulate it or roll it out to get the x's. Then we're going to do a backward pass to get the lambdas. So that'll give us the lambdas and delta u's. Basically, it's going to give us the gradient respect to u. We're going to take a gradient step on u, right? And then we're going to roll it out again. And if you were doing this on a deep neural net, you would do some kind of weird, weight decay thing. In our case, it's a small problem. You can do it. We're going to do a line search to figure out a good learning rate, step length, whatever. And then we're just going to repeat this. Okay, here we go. Oh no, okay, so the system we're going to do this on is really, really dumb and simple. It's called a double integrator. So it's literally x double dot equals u. You can think about this as just a point mass that you push on with some force, and they use the force. A nice analogy for this is like a brick sliding on ice, like a frictionless brick on ice, and you can push the brick. So these are the dynamics. So I've got an A matrix and a B matrix, and it's in discrete time. Just integrate the velocity. State is position velocity, blah, blah, blah. And it's just doing like really, really simple integration on that. It's in 1D, so it's just sliding on a line. The state's just QV, position velocity. And we're going to try this. Let's see, maybe we'll do 5 seconds first. So 5-second time horizon, 10 hertz sample rate. It's like 50 time steps, 50 knot points. We're going to start it at 1, 0. So this is like 1 meter to the right. And we're trying to drive it to the origin, right? And no velocity, blah, blah, blah. That's the initial conditions. We're going to make up some cost weights. So we're going to put a cost on the state error. So identity matrix cost on the states. So that means I'm trying to drive this thing to the origin, which means I'm trying to drive it to position 0 and velocity 0. I have a little control cost, 0.1 on the controls, and then I have a terminal cost. I just made it the same for all the Q's the same. Cool. So this is just me writing the cost function so I can compute it if I give it a trajectory. This is doing a rollout, right, on those dynamics. Now we're going to make an initial guess. So we're just going to plug in all zeros. So nothing fancy, super dumb. We're going to do initial rollout, compute the initial cost. So that costs like 25.5. Cool. And now here's the main loop. So it's exactly what we just wrote down. We're going to do an Armijo line search in here. We're going to do like a convergence check that's just looking for the gradients getting tiny. This is the backward pass. It's the equations we just wrote down. Those are basically giving you lambda and grad u. And then in the forward pass, I'm going to apply basically take a gradient step with step size alpha on u and do a line search on it to get the new u. So we're going to go ahead and run that. Took about 600, 700 iterations. Cost went down to about 6.6 from 25. Looks good. Let's take a look. So yeah, looks reasonable. It's starting at 0 velocity, a meter away. And it's sort of doing this nice little like slide to the origin, converging to 0 velocity. That's what the controls look like. They kind of peak and then drop down and decay. Cool. This seems super reasonable. We're going to do one more thing just to kind of give you an illustration of why we don't do this stuff anymore. So I did a 5-second horizon. Let's crank this up to like a 10-second horizon. Still a super benign problem. So we're going to do exactly the same thing. Roll it out, blah, blah, blah. Note now it's taken a while. Let's see. Is it going to converge? It's taken a while. Still going. Okay, converge. It took like 2,400 iterations, so kind of a lot, right? And looks pretty much the same, right? It's just converging to 0. I didn't really get anything new out of this. Looks exactly the same, just got twice as much time. If I crank this up a little more, like if I go to like 15 seconds, it's going to start really struggling, and it's going to like probably barf pretty quickly. And this is that tail wagging the dog problem. So think like a deep neural network. Time steps are like layers in the network. The deeper I go, like the more these kind of like ill conditioning gradient, vanishing, exploding gradient issues are going to come and bite me. So these things have like notoriously terrible ill conditioning issues, and you need to play lots of tricks to get them to work well in practice and not kind of do terrible things where they blow up on you. Okay, and that we end at 1:50, right? We're at time, I think. Right, yeah, cool. Okay, so next time we're going to do this another way. In fact, we're going to do this 3 different ways. And by the end of that, hopefully you'll know what Lagrange multipliers mean here and all kinds of other good stuff. Catch you guys next time. Thanks. See ya.